Okay, so so this is the third to last lecture, right? We have today, we have Wednesday, and we have next Monday, and then we're done. I just wanted to give one more corollary about the Morse index theorem, which I didn't get time to do last week. Then we're going to start chapter 12 on Priceman's theorem, which tells you something about the fundamental group of a compact manifold with strictly negative sectional curvature. And that's all we'll have time for, although we've done a lot, I think, in this course. So let me remind you what the Morse index theorem was. We proved it last time. If we have a geodesic on our Riemannian manifold, then we get the index form of the geodesic, which is a quadratic form or equivalently a symmetric bilinear form on the space of piecewise smooth vector fields along gamma, which vanish at the endpoints. And then that symmetric bilinear form could have an index if it has a maximal negative definite subspace. And the theorem says that it does have a finite index. And that index is equal to the sum counted with multiplicities of all the interior conjugate points. So here's gamma of 0, gamma of A. If there's any conjugate points to gamma of 0 in the interior, they'll have some multiplicity. The sum of those points counted with their multiplicities is the index of this bilinear form. So corollary, which is really just a rewriting of this thing, it says the following. This is called the Jacobi theorem. So let gamma be a geodesic. And suppose gamma of A is not conjugate to gamma of 0. So if there are any conjugate points, they have to be in the interior. Then gamma has no conjugate points on 0A, if and only if, for all proper variations, gamma S of gamma with energy function E there exists some delta positive such that E of S is greater than or equal to E of 0 for all S in minus delta to delta. Okay, in particular, if gamma is minimizing, then gamma has no conjugate points on 0A. So before I explain how this is, where's my chalk? This is just a rewriting of the Morse index theorem. It's worth pointing out, because I've been trying to do that all term, when Do Carmo does things that are non-standard or incorrect or just lacking in details. For some reason, in Do Carmo, instead of writing this, he writes E of S less than E of delta in Do Carmo, which is clearly a typo. This makes no sense at all. Okay, so if you're reading the textbook, just be aware this is an obvious mistake. Okay, so why is this true? This is just, as I said, rephrasing the index theorem. So by the Morse index theorem, gamma has no conjugate points in the interior if and only if the index of IA is 0. That's exactly what it says. So there does not exist any negative definite subspace of this script V, which was the piecewise smooth vector fields that vanish on the endpoints. I guess strictly speaking, any non-zero, because by the definition of negative definite, the 0 subspace is both positive and negative definite for any bilinear form, because there are no 0 vectors in it. Also, since gamma of A is not conjugate to gamma of 0, there's no radical. the radical of IA is also 0, right? Because remember, one of the preliminary steps in proving the Morse index theorem, we showed that the radical was exactly equal to the Jacobi fields, right? So and that means conjugate. That means gamma of A would be conjugate, right? So since gamma of A is not conjugate, there are no Jacobi fields on gamma, so there are no Jacobi fields which non-trivial Jacobi fields which vanish at the endpoints, which exactly means that the radical of IA on V is 0. So then we claim that so this A and B. So B is immediate because of our assumption that gamma of A is not conjugate to gamma 0, and A then is now equivalent to the index being 0, to the having no conjugate points. So A and B implies that IA is positive definite on V. So we essentially did this in the course of proving the index theorem, but I think it's worth doing again because it's just a few lines and it's more general than what I did last time. So since there exists no negative definite subspace, for all V in script V, IA of V has to be greater than or equal to 0. So here's the proof of the claim. Okay. Well, then we want to show that IA of V equals 0 implies V equals 0. Right? That would tell us that it's positive definite because we know it's always non-negative. And if the only time you get 0 is if you put in 0, then you're done. Well, we can compute this is equal to IA of V plus 2 lambda IA of VW. So I'm abusing notation. Maybe I shouldn't be doing that. I'm identifying that the quadratic form and the bilinear form, but I shouldn't do that. V plus lambda W VV. Okay, so this is greater than or equal to 0 because this is true for all vectors because there's no negative definite subspace, and this is 0, and therefore, as in last class, this is for all lambda. The only way that this will be non-negative for all lambda is if IA of VW equals 0, but then V is in the radical, and that means that V is 0 because there's no radical. So this is a linear algebra result. It says if you have a symmetric bilinear form on some vector space, even if that vector space is infinite dimensional, if you know the radical is trivial and you know there's no vector that you can plug in there into the quadratic form and get something negative, then it has to be positive definite. Okay, so that's the proof of the claim. But then, so hence, no conjugate points on the interior is equivalent to IA is positive definite. But then that's exactly what this corollary is saying for us, right? That what is IA is the second derivative. So E double prime at 0 is positive definite for any variation gamma S of gamma with energy E. So gamma, so S equals 0 is a local min of E, and that implies that E of S is greater than or equal to E of 0 for all S close enough to 0. Okay, yep. Where did I? That does not exist. Does not exist any non-zero negative. That's what it means for the index to be 0. There's no non-zero vector in script V that you plug into the quadratic form and get something negative. Okay, so that proves That proves this, right? In particular, so having no conjugate, if A is gamma of A is not conjugate to gamma of 0, then having no interior conjugate points is equivalent to every variation of gamma, every proper variation of gamma, as it gives you a local, gamma is a local minimum for every proper variation, right? So if gamma is minimizing, then of course gamma is a global minimum for the energy, and therefore it's satisfied. Then it's a local minimum, and therefore there's no conjugate points. So in particular, if gamma is minimizing, then E has a local min at s equals 0 for any gamma s variation, proper variation. So so the index equals 0. So there's no conjugate points. There's no interior conjugate points. Okay, and the corollary of the corollary, which is just the contrapositive, the geodesic gamma, let me just say, call it gamma, is never minimizing past its first conjugate point. Right? And this is the contrapositive of the previous. Right? Because if there was a conjugate point, I mean, if it is minimizing, there are no interior conjugate points. So if there's an interior conjugate point and you go past it, then it can't be minimizing. So assignment 4, question 1 is this, right? But you're not going to prove it like this. This is a direct proof of this. I walk you through it, right? I give you all the hints on how to do it. And this is a sort of long-winded way of getting the same result as assignment 4, question 1. But of course, the Morse index theorem gives us much more. And then the other corollary of the index theorem, which I did do last time, was that the set of this was a corollary of the proof, not of the statement. The set of conjugate points along a geodesic is discrete and therefore finite. So I did that last time. All right, any questions before we change gears completely? Yeah. 0A. I mean, I'm being, the conjugate points are on the geodesic. That means gamma of t is not conjugate to gamma of 0 for any t in the open interval. All right. So we are moving on to chapter 12, which is the last thing we're going to do. And as I said, this is a result about the fundamental group of a compact manifold with negative curvature. It's called Priceman's theorem. But before we actually get to that, we're not going to get to that till Wednesday. We're going to need some preliminary results, which are actually pretty general. This is chapter 12, the fundamental group of compact Riemannian manifolds with negative curvature. So I'll tell you what the theorem says today in a few minutes, but we won't get to the actual statement and proof till Wednesday. So let's set it up. So suppose I'm going to start out more generally, right? Eventually we're going to look at just compact, and we know compact is always complete, right? But for now, let's just assume it's complete, but not necessarily compact. So suppose MNG is complete with negative sectional curvature. Right? Not constant, could be, but it doesn't have to be constant. It's just that for every point in M and any two-dimensional subspace of the tangent plane, the sectional curvature at that point in the direction of that two plane is negative. Then the universal cover M tilde of M equipped with the covering metric G tilde, which is pi star of G, is simply connected. That's what the universal cover means, right? This is some fact from algebraic topology that every manifold, there's more general than that, but every smooth manifold has a universal cover unique up to diffeomorphism, up to homeomorphism, which is simply connected. Simply connected, and is simply connected, and the metric is complete with sectional curvature K tilde negative, and pi from M tilde to M is a local isometry. Now, these are just facts that we've used before, especially on assignment 3. There was a lot to do with this universal cover and the covering metric. So this was a big deal, right, in assignment 3, that if you do have a covering map, then so this is a covering map, then pulling back a complete metric by a covering map gives you a complete metric. And because this is the universal cover, this is simply connected. And the covering map is always a local isometry by the way we defined G tilde. And why is and because it's a local isometry, that's why K tilde is also negative if K is negative. Okay. Hence, by the Cartan-Hadamard theorem, M tilde is diffeomorphic to Rn. In fact, all we needed was K less than or equal to 0 for that. In fact, this only needs K less than or equal to 0. Right? We proved the Cartan-Hadamard theorem says if you have a complete Riemannian manifold with non-positive sectional curvature, then it's diffeomorphic to Rn. Okay, so what we want to do in this chapter is we want to study pi 1 of M, the fundamental group. That's it's a group, and it's defined as the equivalence classes of homotopy closed loops centered at some point, right? Really, strictly speaking, I should be talking about pi 1 of M P, where P is some fixed point in M. All our manifolds have been connected for like half a term now. We're only going to be thinking about connected manifolds. Pi 1 of PM, this is the equivalence classes or homotopy classes. Homotopy classes of loops at P. That means continuous paths that start and end at P. And you can define what it means for two such continuous loops at P to be homotopic, and that gives you an equivalence relation, and you can show that the set of equivalence class has a group structure by concatenating loops. You get another loop, and the homotopy of the concatenation. Sorry, if two. So you've hopefully seen this, and if you haven't, it doesn't matter. If gamma is an equivalence class of loops, let's call them G. G1 concatenate G2, that's equal to the equivalence class of the concatenation, etc. Okay, this is something you see in a topology class. So why do we want to study this? So I'm saying equal, right? You define this for every point P and M, you define this. And if M is connected, then all of these guys are isomorphic to each other as groups. right? But not canonically. You have to pick a path from P to Q and get your isomorphism, and that isomorphism depends on the path. So here's a fact. If the universal cover of M is Rn, which it is here. So let me say of a manifold M, which it is here, then all the higher homotopy groups are trivial. So pi k of M is 0 for k at least 2. So you either know what higher homotopy groups are or you don't. If you don't, you can ignore this. Don't ask me why this is true, because I've never seen why this is true. This is in fact. We usually say 0 here instead of 1 because the higher homotopy groups, unlike the fundamental group, they're abelian, right? You should think of these as equivalent homotopy classes of continuous maps from the K sphere into M, right? Because these are really homotopy classes of continuous maps from the one sphere, S1, into M. And it's not obvious that these have to be abelian, and these are very hard to understand. But in this case, when our manifold is complete with negative sectional curvature, then it is covered, universally covered by Rn, so it doesn't have any higher homotopy groups. So all the homotopy theoretic information in this case is contained in pi 1, right? Because it's connected, so pi 0 is trivial. Pi 1 is the only one that could be non-trivial. Of course, that's not all the topological information, because you can have such manifolds with non-trivial homology or cohomology. It's just the homotopy theoretic information. Okay. So what we'll prove on Wednesday, next time, Priceman's theorem. If Mg is compact with negative curvature, so it's exactly this situation we have here, except I'm adding the compactness assumption, which is stronger than completeness. Then every non-trivial subgroup of pi 1, non-trivial means i.e. not equal to the trivial subgroup or the whole thing, is infinite cyclic. So there'll be a bit of group theory in the last 3 lectures of the course. So that's what we're going to prove. So an example, if we take T3, which is the 3 torus, then something you learn in algebraic topology is that pi 1 is Z plus Z plus Z. Okay. And now there definitely exist subgroups of this group, which are not, trivial, which are not infinite cyclic, because I can take that, right? I can take any 2 of these. That gives me a non-trivial subgroup, which is not infinite cyclic. So T3 does not admit any metric of negative curvature. Right? T3 is compact, so any Riemannian metric on there will be complete. And if it was strictly negative curvature everywhere, then by Priceman's theorem, you couldn't have a non-trivial subgroup of the fundamental group, which was not infinite cyclic. But since you do, there is no metric of negative curvature. That means if you put any Riemannian metric on T3, there has to be at least one point where the sectional curvature is either 0 or positive. So if G is any metric on T3, there exists a P in M and an LP two-dimensional subspace of TPM such that K of LP is either 0 or positive. Okay. That's a consequence. We're also going to prove a very similar result. So we'll also prove if MG is compact and K negative, then pi 1 is not abelian. Okay. So in particular, so Tn for n bigger than 1 has no metric of negative curvature. Because pi 1 of Tn is Z is abelian n copies. Wait, why did I don't need to make n bigger than 1. Okay, so any torus, in fact, any metric on the torus has to have at least a point and a two-plane where the sectional curvature is non-negative. Of course, on T1, we know it's flat. Any Riemannian one manifold is flat. Was there a question? Virtual?
Yeah. Do you have any examples of compact manifolds with negative curvature that are kind of easy to visualize?
I do not. The question is, do I have any examples of manifolds, compact manifolds with negative curvature that are easy to visualize? I don't, but let me think about it and I'll tell you next time. Right, because we remember we proved Meyer's theorem that says if the curvature was positive everywhere, then it had to be compact. But that wasn't an if and only if, right? Just because your Riemannian manifold is compact doesn't mean the curvature has to be positive everywhere. There do exist compact manifolds with sectional curvature negative everywhere, but right now I don't know the answer to that. So let me get back to you. Pseudosphere is not compact. Yeah, there's lots of easy examples like hyperbolic space has constant negative sectional curvature, but it's not compact. Okay, and then if time permits, on Monday of next week, we'll prove Bayer's theorem, not to be confused with Meyer's. Bayer's theorem, which is a refinement of Preissman. It says, again, with the same hypotheses as Preissman's theorem, I might have spelled it wrong, that in fact, it's not just that it has to be infinite cyclic, you learn more about it involving solvable subgroups and normal subgroups. And so I'll state it on Monday when we get to it. I think we'll have time to get there and then we'll stop there. So, but first, we're not going to do any of that today. So first, we need a general theorem, again, due to Cartan, about existence of closed geodesics in a compact Riemannian manifold. Okay, so first I have to tell you what does it mean to have a closed geodesic before we state the theorem. Actually, I'm not going to do that yet. We need to talk a little bit And maybe I can do that first. Okay, no, let me do this. So before we do that, we need to understand a little bit about this isomorphism between the fundamental group and the group of deck transformations of the universal cover. So I'm going to just tell you some facts from algebraic topology, which we're going to use, but I don't know if we're going to get to them today. But we should go over them right now. So okay, so MG complete, M tilde, G tilde, the universal cover with the covering metric. So G tilde is pi star of G, and pi is a covering map and a local isometry. We said all this before. So let's let A of M tilde be the group of deck transformations. He calls them covering transformations. Most authors call them deck transformations of this covering. So it's the group of all diffeomorphisms such that pi compose F equals pi. Okay, that means that it takes the sheets of the covering to themselves. I mean, sorry, not to themselves. It interchanges the sheets of the covering. And here's a fact. If F is in A of M tilde, then F is an isometry. We already did this many weeks ago, and you can see that from here just by taking the pullback on G of both of these things. And moreover, if F is not the identity, then F has no fixed points. So this is a fact about deck transformations, right? There's the identity, of course, and every other deck transformation has no fixed points. And there exists an isomorphism from this group of deck transformations of the universal cover with pi1, with the fundamental group of the manifold. And it's not canonical, but it is going to be important for us how it's defined. So I'm going to tell you how this isomorphism is defined, and you can just believe that it's an isomorphism, or you can check the details yourself, because that would be just a bunch of algebraic topology. So as this isomorphism is defined as follows. Choose a point P tilde in pi inverse of P. So P tilde is in M tilde, and pi of P tilde is P, right? So first of all, I'm identifying this group of deck transformations with the fundamental group at a particular point, right? If I chose some other point, P prime, there'd be a different isomorphism. But not only that, the isomorphism depends on the choice of a P tilde lying above P. So this is a picture of M tilde, and this is a picture of M. So given an equivalence class in pi1, this is a homotopy class of loops at P. We associate a map, a deck transformation, alpha, which depends on this P tilde that I chose, right? And now it's going to be a map. G goes to alpha p tilde g. So this is in pi 1 of MP, and this is going to be in A of M tilde. So I have to define what this map is. So this is in A of M tilde by as follows. So let Q tilde be a point in M tilde. I have to say where it goes. Okay. Choose a path sigma tilde in M tilde from Q tilde to P tilde. Then sigma, which is pi composed sigma tilde, is a path in M from Q to P. So Q is pi of Q tilde. And this, of course, is pi of P tilde. So I have Q, and this is sigma. And I have, remember, G is my loop. This is a representative for that loop. It doesn't matter which one you choose. Let beta be, first you follow sigma, then you follow G, and then you follow sigma inverse. This is a loop at Q. So this is concatenation of paths. Concatenation of paths. And a lot of algebraic topologists will write concatenation of paths. The first one is on the left and then on the right, and then you go like that. That just psychologically disturbs me because I'm thinking of whatever comes first should be on the right. But anyway, it means you follow sigma, then you follow G, and then you go sigma backwards to Q. So that's a loop on Q, at Q. And then since pi is a covering map, there exists a unique lift beta tilde Q tilde of beta starting at Q tilde. Right? If I take this thing now is beta tilde going here, beta is going here and then around and then back. If I have any path downstairs, doesn't have to be a loop, but any path downstairs, and I pick a point above the initial point of my path, then because it's a covering map, there will be a unique lift of that map starting at that point, but it doesn't have to end at this point, right? Just because I lift a loop doesn't mean it ends at a loop. So then we define, I'll go over here because I have more to write. We define alpha G P tilde of Q tilde to be the final point of the lift. So I've parameterized all these paths on 0, 1. Okay, so I have this beta is that guy, and this lifts to beta tilde, and it ends beta tilde Q tilde. So beta tilde Q tilde of 1 is by definition alpha G P tilde of Q tilde. Okay, so there's so many things you have to check here. You have to check that everything is independent of the choices, right? The representatives. So if you had some other path homotopic, all this thing, G, I picked a representative. So there's a lot of things to check here, and that this is an isomorphism. So this exercise, or just read it or just believe it, this is well defined and gives an isomorphism. Isomorphism between pi 1 of M based at P and the deck transformations of M tilde. So as I said, like we're going to need this formula either later today or early on Wednesday. But if you're just willing to believe this algebraic topology, then you don't have to sweat out the details, right? This is all we're going to need. And just as a observation, if Q tilde equals P tilde, if I want to apply this map alpha G P tilde to P tilde itself, we can take sigma to be the constant path. We can take sigma tilde is the constant path. And that means that sigma is the constant path. And that means that beta is just G. And that means that alpha G P tilde applied to P tilde is just G tilde Q tilde P tilde of 1. Okay, so in this case, if I want to see where this point goes, if I want to see where this point goes by this deck transformation, alpha P tilde of G, I take my loop G and I lift it. There's going to be a unique lift starting at P tilde, and it doesn't have to end at P tilde. And this is going to be alpha G P tilde of P tilde is just G P tilde of 1. Okay, so that also is going to show up when we apply this fact. We're going to end up showing that two deck transformations are the same. And the way we're going to do that is we're going to be able to use this formula on one side and this formula on the other side, and show that they both map one particular point to the same point. And therefore, if you do one and then the inverse of the other, it has a fixed point. And therefore, that's the identity, and therefore they're equal. Okay, so I will remind you of these formulas when we use it. I think we'll get to it today, but if we don't, it'll be the first thing on Wednesday. Okay, so now we're almost ready for the existence theorem on closed geodesics, but we need a definition. A set L of closed paths, continuous paths, in M is called a free homotopy class if it is an equivalence class with respect to free homotopy of closed paths. So what does that mean? So if I have, that is, if F and G are two closed paths, in M, so that just means they're continuous. This is all topology. There's no geometry here, or smooth manifold theory here. They're continuous, and closed means that they end and start at the same point. But these two, the initial and final point of F is the same, and the initial and final point of G is the same, but they don't have to be the same as each other. Then we say F and G are freely homotopic if there exists H from 0, 1 times 0, 1 to M continuous, such that H of 0t is F of t, H of 1 of t is G of t, and H of S 0 equals H of S1 for all t and S. Okay, so this says that it's a homotopy from F to G, but all the intermediate curves are closed curves, but the endpoints could be moving, right? And that has to be the case if the if this point and this point are not the same, there's no way you can homotope them one to the other with the same fixed endpoints. So i.e. H S dot 0, 1 to M is a closed path in M for all S. Okay, so under a free homotopy, the endpoint or the origin H0, HS0, which is equal to HS1, is allowed to vary with S. Okay, so the picture, this could be F of 0 equals F of 1, and then G of 0 equals G of 1, and we get a smoothly varying family. I don't know how I'm going to draw it, but it might go like that. Eventually gets to G. Okay, and one more fact about this free homotopy class, which is almost obvious, but again, I'll leave it for you. So here's a fact. Free homotopy classes of closed paths are or correspond to conjugacy classes in pi 1 of MP for any P. Okay, so in other words, you can look at L, this is a group, right? So it has conjugacy classes. Every point in here, will determine a conjugacy class where two points are in the same conjugacy class if there's an element in the group which conjugates one to the other. And so a conjugacy class in pi 1 corresponds to a free homotopy class of closed paths and vice versa. Okay, so in particular, if pi 1 of M is not trivial, then there exists a non-trivial free homotopy class L. Right? Because remember, for a group, the identity is the only element in its conjugacy class, because if you're conjugate to the identity, you're the identity. And then if you're going to have anything else in pi 1, if it's not the trivial group, it will live in some conjugacy class. An element, a non-identity element, will live in some conjugacy class, which is not the trivial conjugacy class. So there's going to be a non-trivial free homotopy class. This is how we're going to use it, right? Because we're going to want to say, well, you'll see now. We're going to want to understand something about the fundamental group, but we're going to get information about non-trivial free homotopy classes. Okay, so one more definition. Now let MG be Riemannian. A closed geodesic on M is a smooth immersion gamma from S1 to M such that gamma is a geodesic at each, let's see, gamma, such that gamma is locally a geodesic. So what do I mean? I don't want to be too wordy. The S1 is a one-dimensional manifold, right? So I can cover it. In fact, I can cover it by two charts, the domains of which are open intervals. Okay. So if I'm saying that if I restrict gamma to any In fact, all I need to do is pull out 1 point from S1, and then that's diffeomorphic to an open interval, right? So if I remove any 1 point from S1, then restrict gamma to that open interval, it's a geodesic. We know what that means. Okay, but it's a smooth immersion from the sphere. So in particular, so not only is gamma of, well, or let me say equivalently, gamma corresponds to, let me just say it like this. We can think of a closed geodesic as a geodesic gamma on 0, 1 into M, such that not only, does it come back to where it started from, but gamma prime of 0 is, I'll call that thing P, is equal to gamma prime of 1 in TP of M. So this is the additional condition. And this is equivalent to thinking of it as a smooth immersion from the circle into M. Right? So it's not just a loop, a piecewise smooth thing that could have a sharp turn when it comes back to the starting point. It has to do it in a C1 way. So I'll draw a picture. So here's our manifold M. Let's put some holes in it, maybe. So this is the manifold. If we have a smooth immersion of the circle, that means it's going to close up on itself, and the velocity vectors are also going to smoothly close up on itself. So this could be gamma of 0 equals gamma of 1, and gamma prime of 0 equals gamma prime of 1. And it's a geodesic everywhere. That's a closed geodesic. You could also have something that looks like this. Right? Here's a situation where gamma of 0 equals gamma of 1, but gamma prime of 0 is not equal to gamma prime of 1. This is called a geodesic lasso. Right? So it's a closed curve, piecewise. Well, if it's a geodesic on 0, 1, we know it's going to be a smooth curve, but there's no reason for the velocity at the end at time 1 to be the same as the velocity at time 0, even though they're in the same tangent space. So there do exist things like that. Okay, but we're not going to care about these guys. We're going to care about these closed geodesics. And in fact, if you've been working on assignment 4, problem 4, I think it's problem 4 is about, or maybe 3, problem 3 is about these closed geodesics. Okay, so now we're ready for the main result of today. So we're going to need this as a tool to prove Priceman's theorem on Wednesday, but this is a very general result, and it's actually gives you a bit of a flavor of geometric analysis, because we want to find some object with certain properties, and the way we do it is we show that we can find an object with potentially less properties in a relatively easy way using methods of analysis. And then we work hard to show that the thing we found actually has more properties than it seemed to have. Okay, so here's a theorem. This is Cartan's theorem on existence of closed geodesics. So it's the following. Let MG be compact. So I'll point out exactly where we need the compactness in the proof, because De Carmo doesn't doesn't say it. Let L be a non-trivial free homotopy class in free homotopy class of closed paths in M. So there's no way you'll have a non-trivial free homotopy class if the thing is simply connected, right? So we need pi 1 of M non-trivial necessarily. And if it is non-trivial, there will be non-trivial free homotopy classes. Then there exists a closed geodesic in M. Okay, so we can find exactly one of these. Sorry, in L. It's clear that this thing must be non-constant, right? So it must be non-constant because the constant curve trivially satisfies the definition of a closed geodesic, right? But the constant curve is in the equivalence class of the identity in the fundamental group, right? So it wouldn't be in L because L is a non-trivial free homotopy class. So it says, essentially it says, if your manifold has some holes in it, compact Riemannian manifold, then if I choose, for example, this guy, which is not homotopic to 0, right? Then it defines, it's a representative of some non-trivial free homotopy class. I look at all the loops freely homotopic to this one. There's going to be one in that class, which is a closed geodesic. So in particular, if it's a geodesic, it's going to be smooth, right? And these guys are all just continuous. Okay, so how are we going to do this? Well, as I said, we're going to construct it in a sort of relatively easy way using analysis. We're going to construct the sort of candidate curve, and then we're going to have to prove that that curve actually is the one we want, does have the properties we want. This is not necessarily unique. Okay, I think I can do it. Okay. So let's let D be the infimum of the lengths of all piecewise smooth curves. In fact, I can make them continuous, it doesn't matter. Smooth curves in the class L. Okay, so we know L is a non-trivial class. It's not empty, right? There's some closed continuous paths in there, and I can always then approximate them if I want by piecewise smooth paths. The lengths are always non-negative of any curve, right? So this is a non-empty set of non-negative real numbers. So the infimum exists. D is greater than or equal to 0, right? Since M is compact, this is where we use it, right? Docarmo doesn't really mention it. There exists delta positive such that every point P in M lies in a totally normal neighborhood W delta. Okay, so because I can certainly put every point lies in a totally normal neighborhood. By compactness, I can cover it by finitely many, and I can just take the minimum of all those deltas, and it'll be positive. So hence, this implies that D is positive. So why? Because if D is 0, then there exists some piecewise smooth path let's say alpha, in this class L closed path with the length of alpha less than delta, this delta here. But that means that alpha is contained in a geodesic ball. That means that alpha is homotopically trivial. But that's a contradiction because alpha is in this non-trivial free homotopy class, right? The only homotopically trivial closed paths are going to be in the trivial free homotopy class, the one of the constant path. Okay, so this is where we use the compactness to argue that D is positive. Okay, and we're going to see where we use the fact that D is positive in a few minutes. And in fact, it's important to remember this because after we do the proof, I'll show you an example where the theorem fails in the non-compact case without going through the details. And it's exactly because this infimum is 0 in the non-compact case. Okay, so now let gamma k be a sequence of piecewise smooth closed paths in L such that the length of gamma k goes to D as k goes to infinity. Now, of course, I can do that because of the definition of D. D was the infimum of all these lengths. So if the infimum is D, that means there's a sequence in this set whose lengths go to D. So this is by definition of D. And remember, we've shown D is positive. Without loss of generality, we can suppose that each gamma k is a broken geodesic on 0, 1, parameterized proportionately to arc length. So why can we do this? We've done this before. I can cover my, if gamma k is not like this, I can cover gamma k by finitely many totally normal neighborhoods, and I can replace, I can just choose points in these intersections, and I can replace, because this lies in a totally normal neighborhood, there's going to be a unique minimizing geodesic, right? So I can replace each of these segments by a minimizing geodesic. Then it's a broken geodesic, right? There's a finite collection of geodesics there that are attached at points where it might jump in the velocity, and the length can only decrease if I do that. So that's even better. And what do I want? I know the lengths are always at least D, and I know they're going to D, right? So if for each k I replace it by one of these broken geodesics, the length is still going to be at least D, and it's going to only get below. So by the squeeze theorem, these new gamma k's, which I'm still going to call gamma k, are still going to go to D. And of course, since it's a broken geodesic, at each point the velocity is constant. I can just reparameterize it proportionally to arc length so that it's in its domain is the closed 0, 1. So that's fine. Now let's let L be the supremum over all k of the length of gamma k. Certainly this is finite because these gamma k's are going to D. So it's a convergent sequence, so it's bounded, right? The lengths of gamma k's are going to D. And this is equal to the supremum over k of gamma k prime, right? These all have constant speed. That's right, because I parameterized them proportionally to arc length, right? So the speed is constant. So for each k, this gamma k has a constant speed, and the speed is equal to the length, because the length of gamma k is equal to the integral from 0 to 1 gamma k prime of t dt, but this is constant, so it's just equal to gamma k prime. Okay, so length is equal to the speed. Now let t1 be less than or equal to t2 in 0, 1. And let's look at the distance from gamma k of t1 to gamma k of t2. Well, the distance between these 2 points is going to be less than or equal to the length of any curve joining those 2 points. And gamma k certainly joins gamma k t1 to gamma k t2. So it's going to be less than or equal to the integral from t1 to t2 gamma k prime t dt. But this is less than or equal to L. So this is less than or equal to L times t2 minus t1. But what does that say? Hence, the set of maps gamma k for k in n is equicontinuous, because I showed that they're in fact all Lipschitz with the same Lipschitz constant. L times t2 minus t1. L is a number. Okay. And then since M is compact, again, we're using compactness here. A version of the Arzela-Ascoli theorem says that there exists a subsequence, which I'll still denote gamma k, which converges uniformly to a closed continuous path gamma 0 from 0, 1 to m. So there's various versions of the Arzela-Ascoli theorem. They all require, this family of maps to be equicontinuous, and then you need some more stuff, some compactness. Here I'm looking at maps into a compact metric, from a compact metric space to a compact metric space. And there is a version of Arzela-Ascoli you can look up that works here. So up to passing to a subsequence, which I'll just relabel to be gamma k, we can assume that gamma k converges uniformly to gamma 0. Moreover, gamma 0 is in the same free homotopy class. So you can check that the free homotopies converge. So what am I saying? Basically, each one of these is in the same free homotopy class. So you can pick a single representative in there, and they're all free. Gamma k's are all freely homotopic to some reference loop. And if the gamma k's are converging uniformly, you can show that the free homotopies will converge uniformly. So this guy is in the same homotopy class, but now it's no longer nice and smooth, right? It's just a continuous map. Let's subdivide, as we've done many times, this be a partition such that gamma 0 restricted to tk minus 1 up to tk is contained in a totally normal neighborhood for each k. So it'll be a different one for different k's. It's the same picture I have down there. and let gamma be the piecewise smooth closed curve such that gamma restricted to tk minus 1 tk is the unique minimizing geodesic from gamma of tk minus 1 to gamma of tk for all k. So again, we had our gamma 0, and then we cover it, and we take minimizing geodesic. So then we can ensure that, so gamma would be a piecewise smooth broken geodesic. It's clear that gamma is in L also, right? Because if gamma naught is in L, then this curve is obviously freely homotopic to gamma naught, so it's in the same homotopy class. So the length of gamma is at least D. We're going to show that this is the one we want. We're going to show that the length of gamma equals D, and that it's a closed geodesic, right? Sorry, it's closed. These pictures are bad, right? Should be coming back. It's closed. Gamma is a broken geodesic. Its length at least D. We're going to show two things: that the length equals D, and that it's a closed geodesic, and then we'll be done. Okay. So suppose that the length of gamma is bigger than D. Well, then let epsilon be the length of gamma minus D over 2k plus 2n plus 1. This is n here. And that's positive. There exists some k natural number such that the length of gamma k minus D is less than epsilon, because remember, the lengths are all above D and they're going to D. So eventually, as long as you go far enough out, the length of gamma k minus D will be as small as we want. And the distance from gamma k of t to gamma 0 of t is less than epsilon for all t in 0, 1, and that's by the uniform convergence of the gamma k's to gamma 0. Okay, so I've got these two inequalities. Let's let gamma j k be sorry, I shouldn't have called these k's, right? I didn't call them k. I did, because k is my index for my sequence. So I'm going to call those j's. It's not dangerous what I did here, but it will be now. So let gamma kj be gamma k restricted to tj minus 1 tj. This is the decomposition of 0, 1 for gamma naught, which gave us gamma. We're just fixing that decomposition in the middle board, okay? And we're restricting each of the terms in this sequence, these gamma k's, to that subinterval. Let's look at the sum from j equals 1 up to n of the length of gamma kj plus 2 epsilon. Well, that's equal to, if I add up all the lengths of these pieces, that's equal to the length of gamma k plus 2k epsilon, because I have 2 epsilon, 2n epsilon. And that is less than d plus epsilon plus 2n epsilon. This is because of because the length of gamma k is less than d plus epsilon. That's here. The length of gamma k is less than d plus epsilon. And then this is equal to d plus 2n plus 1 epsilon. And that's equal to the length of gamma because of the definition. If you solve this for length of gamma, you get exactly that. And this is the sum from j equals 1 up to n of the length of gamma j, which is the same decomposition for gamma. Okay, so what have we got? We have the sum from j equals 1 up to n of the length of gamma kj plus 2 epsilon is less than the sum from j equals 1 up to n of the length of gamma j. Okay, so at least one of these guys has to be less than that, than the corresponding one there, because if for each j, this guy was at least equal to this one, then the sum here would be at least equal to the sum here. So there exists some j naught from 1 up to n such that the length of gamma j naught k length plus 2 epsilon is less than the length of gamma j naught. But this contradicts that gamma j is minimizing on tj minus 1 up to tj. Okay, so hence we got this contradiction by assuming that the length was bigger than d, therefore the length equals d. Do I have time? So hence the length of gamma equals d. I don't know if I have time to do this. So it remains, so now parameterize gamma by arc length. So we have gamma from 0 to its length L to M is a broken geodesic. That means the velocity can jump at a finite number of points, which has minimum length L in the free homotopy class. Script L. So all that remains to show is that it's regular. It has no jumps in its velocity. And then we'll be done. It'll be a closed geodesic. So we'll show that gamma is regular. In other words, C1 at the points Tj, which is gamma of Tj for j equals 1 up to n. And that implies the gamma is a closed geodesic in the homotopy class L. Okay, so that's all that we have left to do. And this, in 2 minutes, is going to finally use the existence of geodesically convex neighborhoods, which we did at the end of chapter 3. So suppose not, let Pi, the gamma of Ti, be a point where gamma is not regular. So the velocity jumps. And let B be a geodesically convex neighborhood of Pi. So here's the picture. There's gamma, some closed curve. I mean, it might have other jumps too, but we're assuming it has a jump at pi. That's why there's a non-zero angle here. So let's choose. I just need 90 seconds. Choose Q1, Q2 in the image of gamma J intersect B such that the geodesic triangle PI Q1 Q2 is homotopically trivial. This uses the geodesic convexity. Remember, one of the applications of the geodesically convex neighborhoods was to get a covering by they're convex. And so here's Q1, Q2. This is a geodesically convex neighborhood. So that means there exists a minimizing geodesic between Q1 and Q2, and it lies entirely in B. So the closed curve given by the minimizing geodesic Q1, Q2, and the arc of gamma that does not include pi has strictly smaller length and is in L, and that's a contradiction. So rather than write anymore, I'll just see on the picture. See, if there was a sharp corner here, then I get this triangle like this. And I know that because this is a geodesically convex neighborhood, this is the only curve from here to here that minimizes the length from here to here. So since this is a curve from here to here in B, this length is strictly longer than this. So if I take this guy and then this together, I get a closed curve. It's clearly in the same free homotopy class because I can free homotope this down to here because this is homotopically trivial, and the length is strictly smaller. But that contradicts the fact that the length of gamma was D, and which was the minimal it could be. Okay, so we're done. I proved the existence theorem. Sorry, I'm over. On Wednesday, I'll just restate the theorem and make some remarks about it, but I didn't want to leave the proof in the middle. And then we'll get to Priceman's theorem. Okay, so I'll answer your question, if not today, then tomorrow on Piazza, because I'm pretty busy today, but I'll find you an example.